All right, it's a pleasure today to have Dr. Alex Ditter. Alex received his PhD from the University of Washington. He was then a postdoc with David Hsu at Lawrence Berkeley National Labs, and then became Beamline responsible for Sector 7.0.1.2. And he's going to be telling us today about, as his title shows, fast scanning transmission X-ray microscopy. With that, Alex, we look forward to your seminar.
All right, thank you. So what I'm going to be talking about today is I'll give kind of a brief intro to our beamline, which is a STXM and ptychography beamline. So I'll explain how those work. I'll talk about the beamline itself and show some experiments to kind of give you an idea of the kind of science that goes on there. And then I'll talk about some of these upgrades we've been doing recently for fast scanning transmission X-ray microscopy. And I've kind of shoehorned in a data analysis project here as well. Then we'll talk about some examples of this data, what we're actually able to collect using this, including a partially lithiated iron phosphate sample that we run in situ. And then I'll talk a little bit about how this is going to make changes at the ALS-U. And so I will just have a little disclaimer here that a lot of this is fairly fresh. And so, yeah, it may not be in its final form right now. So bear with me on that. So with that, first we'll talk about the beamline and the techniques that we're doing. So if you're not aware, STXM stands for Scanning Transmission X-ray Microscope or Microscopy. And it's kind of convenient in that the name describes exactly what it is. So we are scanning the sample through the X-ray beam. Let me do a pointer. So we're typically scanning the sample here through the X-ray beam, or you can scan the focusing optic across the sample. We're measuring transmission, so we're looking at the transmitted X-rays through the sample, and these are collected typically with a photomultiplier tube or a diode. And then we are using monochromatic X-rays, so this lets us do mapping, this lets us do spectroscopy, and it's a microscope. So we're focusing using this zone plate, which is essentially a circular diffraction grating, down to tens of nanometers, depends on the exact characteristics of the zone plate, what your focal spot size will be. And this builds up a high resolution image. So this doesn't really tell you what the data you get out is. So the kind of simplest data is just a single image, this contrast image here I think this is at the oxygen K edge. This is a fib stub of uranium oxide. And so what we're looking at here, basically the darker parts of the sample are absorbing more, and you can see some of these features. So for example, the platinum here, which is from the fibbing, and then as well, you can see kind of different species within the sample based on the intensity there. As I mentioned, we can do elemental maps. So here you're taking one image on resonance and you're taking one image off resonance, and then you're subtracting the two. So for example, at iron, this map was probably taken at about 708 EV and 704 EV or something like that. And then you subtract those two images. And this gives you the location of the iron in the sample. And then the other thing you can do is what we call a stack of images. So here we're taking a single image, like as in the first example, but then you change the energy and you repeat this image and you do this over and over and you build up this 3D data set that we call a stack. And so basically you can think of this as each individual pixel of this image also contains a spectrum an X-ray absorption spectrum. So this is demonstrated here. So basically you look at this region and we'll get one species of uranium oxide here. This is, I believe, a uranyl species. And then this bulk kind of region, what I've labeled bulk on the left here, this other region is a different uranium oxide species. And so here we're doing spectral microscopy, we're doing kind of chemical imaging, basically. So to talk about ptychography, I'm not going to go into every detail on how this works, but you can think of it as you're doing essentially a very similar measurement to STXM, but instead of just a simple diode behind it, you have an area detector, for example, a CCD. And so what this lets you do is not just collect the transmitted light, but also collect the scattered light. And from there, you can use a phase retrieval algorithm to reconstruct both the probe, so you get an image of what your X-rays actually look like incident on the sample, but also, probably more importantly, you get an image of the sample itself. This is kind of, it gives you very similar data to STXM, with the exception that you also get phase contrast. So it's not only the absorption, but you also get the phase change across the sample. And the one thing to note here is that it's a higher resolution technique. That's the whole point of it, is we're kind of able to reconstruct to a finer than the spot size of the beam. This is, it requires many more photons, and so your sample needs to be hard to X-rays in order to do this without getting damaged. And so I'm not going to go into too many details about how the actual phase retrieval algorithm works, but if you're interested, this article by Pfeiffer, I think, is quite a good one. Okay, so the traditional STXM, what I'm calling the traditional STXM, we have a few of them here. It's kind of this big box structure, and you may see these at other synchrotrons as well. It operates under vacuum. It also can operate under helium because there is an X-ray transmissive window inside of it. So it can go up to 200 torr. And this is the kind of STXM where you're scanning the sample through the beam. So the X-ray beam is focused to a spot and the sample is scanned through that spot to build up your image. This gives it kind of a several millimeter scan area. Based on, you have a fine piezo stage and of course, I think also piezo stage in our case. You read out the position using an interferometer, and then again, you collect the transmission via a diode or a PMT. So this is kind of in comparison to what we have at 7012. You can see, well, actually, I haven't put anything for scale, so you maybe can't see, but the size of this chamber is much smaller. The X-rays here are coming in from the left, and the sample is loaded through a CompuStage holder, which is the same thing that you would see on a TEM from like Thermo Fisher. So what that lets us do is we can basically use the established sample environments that they have from various companies for working in a TEM. And so we can kind of have all sorts of flow cells and whatever you might want here in terms of that capability. The other thing that's different is we also have a CCD on the back, and this is for doing ptychography, like I had mentioned before. And so this, essentially, we have a diode in here as well for doing STXM. But we also, have this CCD detector. What we're doing, because the CompuStage cannot move the sample very quickly and we can't add a piezo motor onto it, we are instead scanning the zone plate. And this lets us scan a little bit faster because it is less weight than the typical sample holder. And we do have interferometers on this one as well, but we basically only use them for diagnostic purposes. For getting the actual positions, we just use the piezo encoders. So talking about the beamline itself, we go from 250 to 2500 EVs. And so that is from carbon up to sulfur. And we're kind of best in the middle-ish of that range around these 3D transition metal L edges. So iron is kind of a mainstay of the beamline, but manganese, chromium, cobalt, nickel are all doable. And we do have some earth and environmental science people who often like to do phosphorus and sulfur. The lower end of this energy range is more challenging for us. We're working with an elliptically polarized undulator as the beam is the source. And so this can do polarization basically in any orientation you want, and also circular polarization as well. So we do a lot of magnetism work using that. We essentially do XMCD STXM. So we're using a 45 nanometer zone plate typically. This gives us essentially a 45 nanometer focal spot. And then our CCD sample distance gives us a rough 10 to 20 nanometer ptychography resolution usually. If we bring the CCD in closer, we can get better resolution than that. And this is highly sample dependent, highly dose dependent. If you're willing to sit on it for longer, you may be able to get finer than that. And we're getting about 10 to the 9 photons per second, what that should say, on the sample. And so, as I mentioned before, we're using these TEM style holders. So that kind of limits the effective size that your sample can be, and you're kind of limited to using one of the holders that we have or that we can borrow from the molecular foundry. So this is kind of a limitation on what types of measurements you can do. We're also limited in the size of area. We can access about 1.2 to 2 millimeter by 2 millimeters. And so your typical samples will look like powder or some kind of like maybe microtome sample on TEM grids or silicon nitride windows. You can do fib sections or microtomes attached to half grids as well. So some examples of work that people have done in the past. This is from, I believe, Jongwoo Lim. Yeah, and he was looking at lithium iron phosphate, which is one of our favorite samples at this beamline. And he was doing essentially an operando measurement of this lithium iron phosphate particles. And so he's doing a charging and discharging process during this, and is taking data and able to track the different, essentially oxidation state of the iron, I believe is what edge they were looking at, and able to kind of track how the different phases of this change during the charging and discharging. And so the setup here is kind of, it's got a flow cell, so we're flowing electrolyte through the cell during the measurement, and then there's a bias that you can apply as well. And this is we have a hummingbird holder which does all of this. Another example, this is an ex situ measurement of kind of these particles deposited in some kind of epoxy and then microtomes. And these are battery particles after a certain number of charges. And so we can kind of watch as you start to get these oxygen vacancies appear in the sample. And this kind of affects how well the battery can charge and discharge. And so they're able to see at very fine resolution, these are some ptychography images up here, how this is affecting these particles and where exactly you're seeing this loss of oxygen. And because we're able to do kind of these small, very fine resolution maps, as well as these larger areas, you can kind of watch this happen across length scales. And then finally, I just want to talk about their were some measurements of an alonged meteorite particle, which were done at 7012 in using ptychography. And this I just wanted to highlight because it kind of shows how using the TEM holder really lets us work with multimodal experiments quite well, because basically they can take this same holder and then take it straight to a TEM to do these other measurements that they've correlated. And so here they're mostly focused on the mapping, and we're able to do relatively high resolution maps of several elements of interest, and they've developed also a quantitative method to identify these mineral constituents. So with that, I think we're at the first break for questions.
All right, I'll remind everyone to type questions into the chat. We have a question from Bianca.
Yes, hi. I had just a question to the detection method. You said that you have the CCD and a diode. The question would be like, why this additional diode? Why don't you use your CCD for STXM? There's certainly a reason for this.
Yeah, the diode is much faster, is the reason.
Okay.
Yeah, the CCD
Is it also flux dependent?
Yes, but I think they kind of saturate at similar flux levels, because the diode or the CCD, it's kind of spread over multiple pixels. But yes, I think that it's just mainly for what do you say? It's
Readout
basically
time.
just the time, yeah. Yeah, it's much faster.
Thanks.
Mm-hmm.
All right, Adam, you have a question?
Hi. Hi, Alexander. Really nice presentation so far. I just was wondering whether it's become custom at all at Cosmic to use defocused spot sizes. We found that to be very effective for reducing radiation damage and actually making the measurements somewhat faster.
Yes, we definitely do defocus. So our normal spot size is 45 nanometers, and when we're doing ptychography, we typically run about 200-ish nanometers, 1 to 200 nanometers.
Thank you.
So yes, we definitely do that.
Janos, you have the last question of this break, please.
Yeah, so it seems like that your ultimate resolution is about 10 nanometers. And what would it take to go down to nanometer? That would be very, very important for catalysis research, because that, nanoparticles are very important for us. So go to nanometer and maybe even sub-nanometer. So I don't know. What would it take? What is the main limitation? I'm not familiar with this technique, so it's a naive question, but I would like to know.
Yeah, so I think there are two things that help with this. One is more flux. So when we're at ALS-U, we're hoping to push the kind of the boundaries here for how fine of resolution we can get, because the coherent flux is essentially what gives you the scattering, and that is what ultimately sets your resolution. The other thing is you can bring the detector closer, or yeah, essentially you're measuring a wider angular range with your detector. And so this is something we can certainly do, but I don't think I think the best we've gotten is probably around, I think we have a paper which claims 5 nanometers, but we often have discussions of sorry. We often have discussions about what does that actually mean? Can you actually resolve features at that length scale or not? So yeah, the standard kind of definition is a little bit suspect as well. But yeah, we're hoping to get down, but possibly not that low. Yeah.
Thanks.
All right, I lied. One more question, a quick one. Stefan?
Hey, Alex. Yeah, this is a quick question. I was just wondering if I know you've done a lot of work with the lithium iron phosphate battery materials, but the lithium K-edge is not easy. Sodium K-edge would be awesome, though. I mean, it's
Yes.
such a perfect energy regime for these beamlines. So, and a lot of people are looking at sodium battery materials now, since sodium is much more abundant. Have you guys thought about trying to look at some of those?
We haven't had any users who have wanted to look at sodium specifically. I'd have to look at the literature to see what the edge actually tells you, because I'm really not familiar with it. But yeah, I think that this kind of right in the middle of our energy range. It would be a great one for us to measure. But yeah, we so far, at least for the year or so that I've been here, we haven't really had anyone trying to do this yet.
Okay, cool.
All right, I'll just comment that, of course, the big funding for sodium-ion batteries just came through a few months ago, so that may well change, Alex, with the big emphasis on sodium-ion in the Midwest, for example.
Great.
All right, you should continue, please.
Okay. So yeah, so now I'll talk a little bit about FastSTXM, both in how we're doing the scans and as well as how we're trying to, in quotes, automate the data analysis, and you'll see what I mean by that later. So there's several motivations for faster scanning. Kind of the most obvious one, which I'm not showing here, is just throughput. You can measure more samples, you can measure larger areas. Kind of related to that is population statistic measurements of, that should say, heterogeneous samples. So if you've got a sample that's got maybe some very rare particles in it or something like that, you kind of need to measure a wide variety of particles to capture these. And so this is something that's been identified by our user community as what they want to be able to do. The other one, and Jerry, you might recognize this image, is that you can do operando experiments at faster rates. So I think the example I showed there was the example I showed a few slides ago was 0.6 to 2 C for battery charging. And so if we can go even faster than that, that would be great. And then finally, and this is kind of one of the probably the biggest motivator, is that the ALS upgrade, we're going to have about 100 times more coherent photons. And so scanning fast is a necessary part of being able to actually take advantage of this and not just cooking our sample. So we're currently not photon limited in most of the STXM measurements at current flux levels, and so we can already take advantage of these faster scans. So most, if not all, STXMs run in a raster scan pattern. This is fairly inefficient for reasons that I'm outlining here on the left. You have an acceleration region, you're kind of doing constant velocity across the sample, and then you have deceleration, and then you return to the beginning of the line. Some people will do maybe a serpentine pattern, which cuts down on this. But there's also just some overhead in starting this motion at all, sending the commands to the motor, getting it to move, etc. In the world of other microscopes, say AFMs or kind of other scanning microscopes, I guess. AFM is the main one that I know of. People have been looking at other ways to do scanning. So this left one is kind of the standard raster scanning, but you could also imagine a spiral. If you're doing a spiral, you're having less acceleration overall, and so you should be able to do that trajectory faster. And then if you're worried about the corners, you can do a Lesagis pattern as well. These are some different options. So we've been working with this group at the Molecular Foundry. They've developed for their AFM a method of doing spiral scanning. And so they have essentially a constant linear velocity at the outside of the sample and a constant angular velocity at the center of the sample. And then they just combine those two spirals to make a pattern, which then kind of spirals back to the middle at the end. And this has worked very well for them. you get essentially very high quality images and you're able to go much faster. And this also respects the instrument limits. So you're kind of you're not telling it to move faster than it can, basically. So for us to implement this, there's a few things that need to come together. One of them is the beamline stability. So right before I joined, I guess a year, almost and a half ago, our upstream mirror was replaced, and it was put on one of these nice granite blocks that really improved the stability and decreased the noise. And so this is, I guess, without context, this is not a useful plot here for you, but this is the power spectrum at our beamline. It looks fairly clean. When we had the old mirror, there were peaks all over the place, and it was contributing to our noise. And so scanning faster doesn't really help you if your noise is quite bad. The other thing is the instrument design. So I've already talked about this a little in comparison with the what I'm calling the traditional STXM. But we've also went through an upgrade of that as well. And so this was really focused on doing the scanning faster. So we've stiffened the zone plate mount. We're not worrying about the interferometers anymore. And we have a new motor controller, this Mad City Labs controller, that lets us do kind of arbitrary motions more easily. And then I'll talk about how we are doing the controls work for this briefly. So we're doing a spiral pattern. As I mentioned, we're working with the Ashby group to use the same pattern that they're using as their AFM. We've also decoupled the measurement timing from the motor position. So if you have a very large spiral image, the motor can really go fast around the edge. And so we can collect many measurement points for each motor trajectory point. But essentially what we're doing is the user will give the same inputs they always give, which are the range, the number of points, and the center of the scan. We have some other parameters that we also insert, so the maximum frequency of the instrument, and this determines our spiral pattern. And so we generate that using this atomic force microscopy code. And then there are some other details. We have to make sure it's not too long or too many points, otherwise our motor controller will not be happy with us. And then we can, as I mentioned before, do this kind of DAC oversampling, and then rebin the collected data into these square pixels. So you can see here kind of what's going on. This blue is the motor trajectory, and each of these red positions here represents a measurement location. And so our goal in doing this was to make it as transparent as possible to the user so that they are basically doing the same thing they've always been doing. And so that has really, I think, helped them warm up to this technique. So just a comparison between the raster scanning and the spiral scanning. These are functionally identical images. The speed up of about 3 to 5 times is typical. I think it depends a lot on the parameters of the scan. If you start doing very large scans, then you start you start losing some of that efficiency because the raster scan actually is fairly efficient for that as well. There just isn't that much overhead. But it's kind of complicated to say exactly how much better we're doing. But for our typical, say, 100 by 100 pixel image, that takes a few seconds, whereas before it was taking maybe 15 seconds or something like that. The other thing to note about these is that, of course, these are no longer squares. And so a lot of the standard image registration techniques don't work. SK image has a phase cross correlation image alignment thing, but it does not work that well in my experience. And so what I've done is basically looked at the paper that they cite there and then just implemented it myself, and that seems to work quite well. So if anyone is curious about how that works, I can share that with you. So we'll change gears here a little bit to talk about another way to make things faster and another bottleneck that we might run into. So this is kind of what I see as the typical synchrotron experimental cycle. You get a grant or a beam time proposal, you prepare your sample, you run your experiment, you do your data analysis, you have a publication, and then that feeds back into your next grant or beam time proposal. In reality, the data analysis really can affect all of this. Maybe you don't publish something and you're just getting some preliminary data for your proposal. Maybe your data analysis tells you that your sample prep needs to change for you to get good data. And then also when you're doing the experiment, of course, you're doing real-time data analysis. And so you're going from measurement back to data analysis. And this is adjusting how you're doing the actual experiment at the time. And so one of the things that really trips up new users is this real-time data analysis, particularly when we're going at the beamline. And so when if you're imagining you're at the beamline, you're trying to learn how to use the instrument, maybe your sample isn't ideal because you don't know what it should be. And so this can make this analysis very challenging for users. And so as we get faster and faster with our data collection, the analysis must become faster as well. And so the aspect of it that I'm going to be looking at here is not really the computational speed of this analysis, but really kind of making it as simple as possible, both so that new users can be successful, as well as making sure that basically you can do this data analysis as quick as possible. So to talk about this, I'll go through a kind of typical data set that we might have. This was some spent nuclear fuel FIB section that we looked at the oxygen K-edge. We use the oxygen K-edge because it's sensitive to small changes in the uranium oxidation state. You can see here U02, U409, U307, those all look fairly different. And so we should be able to use it to figure out the oxygen, the uranium species. So this is what the FIB stub looks like. It's got a small hole that they drilled in it with the FIB. And I apologize, it flips upside down when I do this, but here is our, I think this is just a normal contrast image of this area. And what we did here was k-means clustering. Basically, we identified 6 different regions from nearest the hole to outside the hole. And what's striking about the spectra that we get out from those different regions is that there are these isobestic points. And that is an indication that this fuel has 2 components. And so we kind of already have a fairly good idea of what's going on here. We've got our U02 standard and our U307 standard. And these kind of look very close to the actual data that we're collecting. So we have a good idea of what's going on. But question is, can we do better than that? So this is a pretty typical data set where you've got a sample made up of several, in our case, we know it's 2 different unknown chemical components, and we'd like to figure out what these are and map them in the sample. So PCA is useful for determining these components, or determining components in general, and it's often used for kind of a data reduction methods, like if you're going to use k-means clustering, you can do PCA first to make it faster. And for like filtering as well. But these components don't really look like your spectra, so I'm showing here the PCA results. So you get one component, which looks like the average of all of the spectra in the sample, and then your second component, which is then added or subtracted to different pixels to give you kind of what the best fit is there. So instead, we're looking at non-negative matrix factorization. This is kind of based off of work done previously. But what we see is that our individual pixel spectra are often very noisy, and they have values below 0. And so this is a big problem for us, particularly where the sample is thin. And those areas turn out to be very important for this sample because that's where the sample is also the most oxidized. And so we need a modification to standard non-negative matrix factorization. So I won't go into too much detail about what we've tried, but are kind of one of our naive attempts was basically the most successful one, and that was to use the same algorithm that they do for non-negative matrix factorization, but just ignore the requirement that the data is positive. This you might expect to give you more of these PCA components because you're not limited to just values above 0, but it turns out not to be the case. We're not 100% sure why this seems to work, but it does seem to work quite well. And so when we do this, we can get what we're calling the interfacial component, which is basically U307, and then this bulk component, which is U02. And so these little features here, I'm not showing any of the individual pixel spectra, but these little features here are real. And so we're able to kind of capture details on that scale. And this can be quantifiable. So one big issue that non-negative matrix factorization has is reproducibility. So when we do this, we often get not unique answers. And so this is especially true now that we've relaxed this negative condition. And so basically you can think of this as if you're separating your data into these two matrices that you're multiplying. One of them is the components, one of them is basically the images that we're seeing. You can insert whatever matrix you want here that's invertible, and you will get a just as valid solution here. So what we end up doing is we're using that freedom to constrain the components here. So this kind of plot is something you'll see in PCA a lot, where you're mapping basically one component versus the other. Each dot here represents basically one pixel on the image. And so you're seeing, oh, this pixel is made up of this amount of component 0 spectrum and this amount of component 2 spectrum. The problem that you can see here is that you would want the component, this map, to look like the components are sitting around the axes. And so our components aren't accurate to what the end member states are of the sample. So we've developed a method to determine what this matrix is that will give us these new components, which kind of more closely match the data with still making them positive for the most part. And so once you do that transformation, you get a different one. And this becomes remarkably consistent. You can get inconsistent results if, for example, you start to add too many components or something like that. But this is something that has worked pretty reliably for at least a few samples. So another example, back to our favorite sample here, this is a ptychography stack of partially lithiated iron phosphate. So here we're identifying these different components, which we can then map onto the iron phosphate, the lithium iron phosphate, and then it's hard to see probably through zoom, but there's this red surrounding the sample, which we're attributing to kind of melt or deposition. You can't see it, but this actually extends throughout the entire sample, so it's kind of coating the entire particle, not just the edges that are parallel to the beam. And so what this has done is we've really kind of made, with these reproducibility improvements, we've made this non-negative matrix factorization a more accessible technique. It's kind of as easy to use as, well, I shouldn't say it's as easy to use as k-means clustering, because I think k-means clustering almost always gives you a good answer. And this can give you, this can basically blow up on you sometimes. But other than that, it's kind of how we're trying to improve this to remove essentially decision points that can slow things down and confuse people. So I think with that, we're at our second break for questions.
And indeed, we have a few questions. While everyone is sharpening their minds about PCA questions, which I'm sure will come. Catherine, you had a question?
Yeah, I did. I just wanted to know, when you were talking about using fast charging for batteries on your Beamline, was that more of a you want to try to go fast for charging and see how it goes? or you currently have the ability and just haven't had as many users take advantage of it?
I think we want to try this. We haven't, as far as I know, I'm not familiar with the entire extent of our Beamline's research, at least, but people are not, as far as I know, doing this very quickly, and I think that's because the scans take a long time, and so that's really been our motivation, is that this will enable this type of measurement.
Awesome, thank you.
Mhm.
Okay, Matt Newville, you had a question?
Yeah, hi. Thanks. This is really nice. I would want to be able to ask a question about the non-negative matrix factorization, but I want to come back to the scanning and the speed up you see with spiral or Lissajous scanning. This is interesting for me working at a hard X-ray microprobe as well. But I'd like to hear a little bit about why it's faster. Right, so a spiral scan has a longer path length, right? So is it just that you're pausing less to write, and is that the speed up? And then,
Yeah,
like, sort of related, are you streaming all of the data for a single map into? And
yes.
Right.
Yeah, so I think it is mostly for us just the removal of this overhead of this acceleration and deceleration.
Right.
So the spiral trajectory is longer, but we have it set up so that essentially we have roughly the same dwell time per pixel as you would put in here. And so the main speed up, well, so there's several factors. The overhead removal of each line having to read out, and also the kind of the decoupling of the detector measurements from the motor trajectory positions really lets us go faster as well, because the motor controller won't let us go faster than like 0.3 milliseconds per position that you program into it. And so if we can kind of sample faster than that, we can go much faster for that reason as well.
Okay, thanks. Okay, interesting. Thanks.
Yep.
All right, so that we stay on time, I'm going to say do the last part of your presentation, and then we'll have time for questions after the conclusions.
Okay. Sorry. Go. Okay. So the most obvious benefit that this gives us is simply throughput improvement. And so just as a kind of, people who don't do STXM very often may not know that this is how it works, but essentially for each data measurement that you're taking that might show up in a paper eventually, you're taking many, many, many more images than just that one. So for example, here, this is kind of the simplest sample I could think of, which is just some particles on a silicon nitride window. The first measurement we took was actually X-rays getting through the window, so we didn't even have to go find the window, which is often something you have to do, which will result in many of these images. And then you also have to find the edge so that you can focus on it. You have to tune the beamline. You can see some these kind of spirally pattern in here is because we're getting some regular noise, which we can adjust. And then yeah, some more tuning. I'm not showing it here, but you focus on the sample instead of the window. And then you start the sometimes very arduous process of finding particles that you actually want to measure. So this can be searching through your sample. You can take many, many images here, trying to find the exact right region that you want. And so when you're doing these measurements, this can take kind of hours per sample. Maybe not hours, but you can spend a very long time on trying to find these. And if your scans are fast, then that really helps speed things up more than you might expect. Another reason we might want to do this is something that's very near to my heart, which is actinide particles. So your X-ray absorption goes like, I believe, Z to the fourth. I didn't check this before I put this on the slide, so someone correct me if that's wrong. And so when you're working with heavy elements, this is particularly challenging, especially for soft X-rays. You essentially need very small particles. And of course, you can grind your sample, but for some of the work that I had been doing, for example, nuclear forensics, you may not want to do that. Like, the morphology of these particles may be important as well. And so instead, we can just take very large area scans, and because the scanning is faster, we essentially can get away with not preparing the sample as well, because we have much more area to look at to find particles. So for example, here, we're able to find some clusters of small particles, which turned out to be very good measurements of this sample. So this is kind of a niche application. One that might be a little bit more typical for our users is automating particle measurements. So very often people will come in with particles. These are battery materials, because we do a lot of battery work at this Beamline. But people also bring in things like soils, various other or environmental particles, catalyst particles, that kind of thing. And these are often mounted on TEM grid. And so what we've done here is we've actually done an automated, pretty simple algorithm, thresholding, and then what's called blob detection, which is identifying different regions for us to scan. And then we feed that in to do these scans automatically. And I'm showing 6 of them here, but in this area, we had 75 different regions to measure. And we were able to do all 75 of these stacks in approximately 2.5 seconds per image. And so this was, I think the whole thing took about 5 hours. So that's a pretty substantial speed up over what we would do normally here. And then last, I will just talk very briefly about some operando measurements that we did. This is partially dilithiated iron phosphate, again, our favorite sample. This was in our gas cell without a spacer, so it's open to the vacuum, but the gas cell also has a heating capability. And so what we did was we heated the sample. We had stacks on 3 different regions before and after heating. And so we're able to use these stacks to actually identify the different regions. And so this is where this non-negative matrix factorization came in. You can see it's very robust for this as well. We're able to identify these different components which match up with the literature values. So because there is literature measurements of what we're expecting to see in the sample, it's maybe not that important that we're able to do this. But for a different sample where you don't have that, this may be much more useful. And so these platelets kind of look like this shape here. You can see the actual region that we scanned was much larger than the platelet itself, because this was my first time using this gas cell and I wasn't sure how much it would actually expand during the measurement. And it turns out the answer was not at all. So I could have done maybe a quarter of the size here and gone about 4 times faster than we did. But despite that, we're taking essentially what are 3 energy stacks here. And so we've got one below the edge. We've got one right about here, which is an area of maximum contrast, and we've got one right about here, which is another area of maximum contrast between the 2 species. And so we're able to do that and fit the different species in the sample, which is the lithiated and unlithiated iron phosphate. And these don't appear like they are going to play. These are movies that go from, but that's okay because I have, oh no, they are, okay. So you can see as we heat here, this is one of the components. I didn't write it down, so I'm forgetting which one it actually is. But you can see as we heat, nothing happens for a very long time. And then we start to, in a second, we start to lose some of this component here. And then the whole, it spreads out to fill the whole particle. And so the same thing happens for this one. And I'll just start this movie as well. So we're doing this as we're increasing the temperature, and we're starting to see new phases form here. And as I mentioned, this is still fairly new, so I'm not going to try and interpret exactly what's going on in the sample yet, but this is at least a new result. And so this is something that we can only see because we're able to do these measurements quickly enough. I suppose you could do them if you're doing it more slowly, but it would just take you 5 times as long. And yeah, this is just showing some of those images. And then we can do the same fitting on a ptychography image. And you can see pretty clearly here that these also show up. So with that, the last thing I want to talk about is just that we're hoping to also eventually do this with ptychography. Basically, this is something that people have done before, both in visible light and in X-rays, but it does kind of decrease your resolution. You can see what's going on here. I like this figure a lot. Is you've got this scattering pattern, and then as you increase the speed that you're scanning, you start to blur out this pattern. And so for us, we're going through the ALS upgrade. We're going to need this fly scanning method to work to fully take advantage of the increased flux. And so part of this will be a much faster detector, which can hopefully mitigate this issue that people run into. And I'm not showing it here, but there was a very recent, I think last week, paper from NSLS, which is also kind of related to this. And so then just to go back to this, in order to make the fly scanning ptychography happen, to actually do ptychography 100 times faster, we're going to need increased coherent flux. So I'm putting all of ALS-U in this little box and saying that that's going to happen. And then we have a faster detector, which is also a very complex thing. And then the data processing. If we're able to collect data 100 times faster, we need to reconstruct it 100 times faster. And so right now, our reconstructions are about as fast as we collect the data. And so this will need to use probably high-powered computing resources. But if all of those parts come together, then we can really start to do ptychography very, very quickly. And so just to wrap up, we're a STXM ptychography beamline, does high-resolution X-ray spectral microscopy. We've developed fast STXM. It's currently implemented at our Beamline. It's a speed up of about 3 to 5 times over traditional scanning. And the scanning not only improves throughput, but also enables new area of science by allowing for faster, and I didn't really talk about this, but more complex in situ and operando measurements. And it's a necessary component to fully take advantage of the light that we're going to get from ALS-U. And so with that, I'll just thank people. There are too many people to list here, and I've probably forgotten some of them already. But David Shapiro especially is also involved in this Beamline and has been helping me with this. And people across the ALS who have done a lot of the upgrades that I've mentioned to our Beamline. And so with that, I think we have more questions.
Indeed. Thank you. That was very nice. Stephen, you have the first question.
Yeah. Hi, great talk. Thank you very much. On slide, I think 37, you showed space, like spiral pattern noise. How is there a way to remove that? I know with a raster scan, you're able to do a Fourier transform of the image. Not this slide, I guess.
Oh, this one.
Yes, that one.
Yes.
You're able to do a Fourier transform of the image to isolate the pattern noise. Is there a similar thing you can do for spiral scans?
If I were better at math, I might have a good answer for you. There's kind of a mechanical answer, which is actually our friends at the Molecular Foundry have done a method where they have this overlapping spiral scan. So they essentially have one spiral scan and then they rotate it slightly and do it again. And what this does for them is they can then use this to figure out why they get these, or where they're getting these dips in intensity, because the AFM has this same issue essentially. And so they have an algorithm for this that we're exploring how to use that, because that's one thing that could be quite nice, is it could essentially eliminate this noise.
Okay, thank you.
Okay, we have a question from Bianca.
Yes, hey, about your speed up and the overview that you can get why you need to do so many scans. Is the reason why like big core scans are not possible, is that due to your zone plate scanning, or is there some other reason? Because that would potentially also help if you could get just like one big core scan.
Yeah, so it's mostly that the CompuStage motors are very slow and they're not really designed for doing that kind of scanning. What we're looking at implementing is doing kind of a tiled scan. So you would move to a new sample position, and then you would scan with the zone plate to do essentially a spiral scan there. And we have this working for the standard raster scan, but there's some bug in it for the spiral scan. So we haven't implemented that yet. But yes, this is something that would help, I think, at least, if nothing else, automate this process so that people don't have to click the button and then do a scan and then click the button and do a scan again. And that should speed things up as well.
So you mean it's more about the scanning, not about the zone plate, like about the spiral scan? That's the hindrance, not the zone plate.
It's the limits of our motor. It's only 80 by 80 microns for the fine motor, the zone plate motor, and then the coarse motor, or the sample motor, is just not designed to be able to do this scanning. It's way too slow.
Okay, thanks.
Mm-hmm.
All right, last question from Peggy.
Yeah, hi there. Nice talk. Yeah, I'm wondering if you guys are thinking about ways to mitigate sample beam damage with the increased flux of ALS-U. I don't know what you're thinking about, cryostages or defocus.
Yes. Yeah, definitely. So cryostages, we do have that capability. Maybe I can find this slide. Oh, that stopped my sharing. Sorry. I've ruined it. Okay. But yes, we do have that capability. We have a cryostage. Our vacuum right now is the limiting factor. This kind of limits what temperature we can get to. And so we're working on improving that right now. We've tracked down one of the leaks. It's just on the detector plane, and so we're hesitant to actually fix it. But the other thing is that this fast scanning, I think, will help with that as well. So if you have 100 times more flux, you essentially need to be, if you're scanning 100 times faster, then you're probably doing about as much rad damage as you would in the slower instrument for the data that you're getting. And so, yeah, but yeah, definitely cryo is one thing that we're really going to be focused on before the upgrade.
Great, thanks.
Yeah.
All right, with that, we're at 10:01, which is as perfect as this seminar gets. I'll thank Alex again for a terrific talk, and I'll stop the recording.